All right. Good morning, everyone. Can you hear me well and see the slides?
Yes, sir.
All right. So, where we ended yesterday, we basically talked about uh, something which is already familiar to you. We talked about the basics of the internal structure of the Earth. We said that we can think about we can actually think about two types of layerings when we try to describe the internal structure of the earth. One could be physical, the other is chemical. The chemical layerings goes as crust, mantle, and core. And of course, the mantle has the upper mantle, the lower mantle, and then you have the inner core and the outer core. We talked about the basic chemical composition that you generally find in crust, mantle, and core. We talked about Cl and Cma, and then, of course, iron, nickel present in core. We talked about their physical properties in terms of lithosphere, asthenosphere, mesosphere, and then inner core and outer core. Um, we said how their physical properties are different. We talked about different boundaries between these layers. So if you have any question that you might have, it's the time to ask. Okay, if not, then let us begin today's class. And we said that we will talk about plate tectonics today, and let us address this subject of plate tectonics methodically and step by step. And let us see a bit of history around how the whole concept of plate tectonics actually evolved uh, in the arena of geoscience. Okay. So what you were looking now in the slide is a world map. It's a very famously. I mean, we all are familiar with the world map, and what people when this map was prepared, what stuck to people that it looks like a jigsaw puzzle, as if you can kind of you know bring Africa this way, or bring the whole um, Americas this way, and it kind of fits, as if it looks. Similarly, at many places it looks like a jigsaw puzzle, as if they were together once upon a time and now they have moved apart. So that is when the first concept of continental drift actually came in. So what continental drift means? Continental drift means simply what we have just described, drifting of continents away from one from the another. Okay. So the researchers noted the geographic fit that we have just described. Example, Africa with South America, like the Atlantic formed by the separation of Africa from South America, as if it seemed. So Seuss, a very famous philosopher and scientist, proposed supercontinent by studying fossils, rocks, and mountains. So, what did they study in fossils, rocks, and mountains? I'm going to talk about in a moment. But this was the first, kind of hypothesization of the plate tectonics by thinking about continental drift, that the continents were together and perhaps have been separated. So Wagner and Taylor in early 1900 proposed the continental drift and coined the term called Pangea. Pangea means supercontinent. That means if we think about all those small bits and pieces and the fragments of the continents, and if we kind of imaginary bring them together, the whole landmass that we come up with was termed as Pangea. So, what are the basic uh, proofs, or what were the hints through which the earlier scientists came with this particular model of continental drift. The first one is the geographical fit that we have just talked about. Fossils, we will show you how what were the fossil evidences, mountains and glaciations. We're going to look through these evidences in a moment. So this is the geographic fit. If you bring all the continents together, of course, you know, this is almost a perfect fit. It's not perfect. It's not 100% perfect. You can see there are plenty of spaces where things are like the blocks are missing, but that's another story. But more or less, they kind of fit together. And this whole thing, this imaginary configuration of continents, was termed as Pangea. So now this is the type of fossil evidence. I mean, I'm not going to talk about the actual fossils, what were they, but this is what people have found. Okay, they found similar type of fossils which are present in South America, also present in Africa. So what could be the rationale? So the rationale could be either, you know, the living organism actually thrived in both the continents, and maybe they would have, you know, or if not, they would have swum across each other, or the other possibility would be that these two continents were together, and being in the same kind of paleogeographic area, we had similar biota living at a particular geological time, right? So that was one type of hint. The one of the examples of such fossil could be Mesosaurus, which are early forms of dinosaurs. Okay, and you know, the dinosaurs could not swim, right? So I mean, one of the most logical conclusion could be that these two continents perhaps were together. Now, of course, what you can see, say for example, if you look at the Appalachian Mountains, okay, and which is in the North Americas, and then if you look at the Caledonian Mountains, which is in Scandinavia, in Sweden, okay, it looks as if, you know, they were a single linear mountain chain, right? But now has been separated like a thread, which were together, but then has been separated. And there are many mountain ranges which are pre-drift for that particular continent. You do see such, you know, linear arrangement across continents. So that also provides you an idea that perhaps these continents were together and the mountains actually formed, and later these continents were away from each other, right? Similarly, you can see here the mountain ranges, you know, kind of yeah. So if you kind of reconstruct your reconstruct the paleogeography of these continents and make the supercontinent, you see the Appalachian and the Caledonian Mountains actually quite like fit like a single mountain chain. Okay. Now there was another important evidence. Say for example, what you observe if you are in India. In India, you find glacier beds. Okay, so you don't have to go much further from Bhopal. If you are, say, for example, you know a place called Itarsi. I hope you know, which is in MP, say only 150 kilometers from Bhopal or 180 kilometers from Bhopal. You find glacier beds there, talcher boulder beds, which are product of glaciation. So, do you really think that I mean, we are simply not in a glacial climate, right? I mean, glacier deposits in today's condition is absolutely impossible. You cannot have glaciation in today's environment, which is present in Bhopal, Itarsi, or Jabalpur, right? So, but you still find glacier beds. So, what is the possibility? The possibility is, of course, that particular landmass, when that bed was deposited, was at a higher latitude. Yeah, was at a higher latitude at which these glacier beds were actually forming. And because India, say for example, was in the southern hemisphere, at a very temperate condition, which is very close to the pole, and that is where you have the glaciation, like you see it in Antarctica, right? So, and you see such, and that is where my boulder beds, the glacier deposits got formed in India, and then India actually migrated to the tropical or subtropical area, right? So that is why you find glacier beds in India, in the peninsular India as well. That is also true for South Africa, Australia, as well as in South America. You do see glacier beds which are not possible in today's position where they are actually, right? So that also provides you some sort of evidences that perhaps these continents were at a temperate region where you had extreme cold, where glaciation was possible, and now these continents have drifted apart from where they used to be. Okay, so Alfred Wegener, he is called the father of plate tectonics. Of course, he was someone who was like a sailor. He used to move around in the sea, and he was a meteorologist as well. In earlier days, these boundaries in science was also not very clear. So he's a brilliant man, and he's the first one, by looking at such evidences, what I have just described, proposed the continental drift theory, that the continents were together and then the continents have moved apart, and that is what you do see right now. Now, he has talked about this very early plate tectonics theory, but then he did not really provide any possible mechanism to explain how these continents actually drifted. Okay, he just stated his observations. He said that the continents do drift, and he gave that continental drift model, but he did not really say what was the force behind for such continental drift. Okay, so scientists go to scientific meetings to present their research. When Wegener presented his research to other physicists, they did not agree. Okay, like any new theory, people do not really agree. They wanted to know, how do continents drift? Okay, there was no driving mechanism to support continental drift, and Wegener could not answer how. So his continental drift model was not accepted at this point in time. But later on, of course, with the advancement in science, continental drift model was of course is the fundamental stone of plate tectonics. Now, what we are looking at right now is the Google image of the Earth, right? And I don't know if you have already noticed, what you can see that if you look through the major oceans, you see like a ridge-like feature throughout the middle of the ocean, right? Let's say, for example, here in the Atlantics, you will observe it in the Indian Ocean as well. You can see here like three such ridges are kind of meeting. This is also important. We will discuss it later on. And several places through almost to the middle of the sea, such ridges actually run. Okay, and that kind of brings us to another mechanism, which runs hand in hand with continental drift. That is what we call as seafloor spreading. So the continents are drifting away from each other. So what is happening to the sea in between? So there must be something happening in the sea. So to accommodate the continental drift, what you are observing, that the seafloor is also spreading, right? Or we can say it is the other way around. Because the seafloor is spreading, the continents are moving away from each other. Why the seafloor spreads? That is another issue which we will discuss. But we can think that the seafloor is spreading, and as a result, the continents are being drifted, right? So continental drift together with seafloor spreading completes the picture of plate tectonics. Okay? So continental drift was re-examined in 1960s with new information, and new theory was developed around seafloor spreading. So the supporting evidences for seafloor spreading were world seismicity, volcanism, age of seafloor, and paleomagnetism. And we are going to touch upon them, briefly here, but we will discuss at length about these particular things when we go to the corresponding chapters, right? And combining the continental drift and seafloor spreading, we term it as plate tectonics. So the 1960s is relatively recent. That is where actually the seafloor spreading was proposed. So geology is a new science compared to physics, chemistry, and even biology, if you think about it. People were doing separate studies about earthquakes, volcanoes, age of seafloor, paleomagnetism, and someone had to put it all together. And that is what was done, not by a single scientist, but different people around the world. And when all these things were put together in 1960s, the theory of plate tectonics actually came. Now 1960s is not that long ago, you know. So plate tectonics being one of the most fundamental theories in earth science, you know, if you compare it with physics, chemistry, or any other subjects, you know, most of the major breakthroughs that happened in those subjects happened pretty early. But in case of earth sciences, of course, the most fundamental concept, and I mean, this is perhaps one of the concepts that deserves Nobel Prize, if you like, was coined very late in the history of science, right? So people had some idea in terms of continental drift and seafloor spreading, but then, you know, all the theory put together with all the evidences and the mechanism, the mathematics around it, everything as a sound hypothesis came in 1960s. So before 1960s, that was the theory of plate tectonics was severely challenged. There were other many different hypotheses around it, but all of them kind of went obsolete once in 1960s the theory of plate tectonics actually appeared. So we will talk about now these some of these evidences that supports seafloor spreading. Okay, so what essentially is happening in case of seafloor spreading? If we think about it, say for example, here we are looking at a particular ridge. That is what you know, we have been discussing while we were talking about that satellite image. Or let us look at here. This is the South American plate. This is the African plate, and you can see this is what we call the ridge that we have just seen. It's called the Mid-Atlantic ridge. Now, such ridges are also called the Mid-Oceanic ridges, or MORs. MOR, or Mid-Oceanic ridge. Okay, so that is the spreading center. That is where the seafloor actually starts to spread. So let me tell you what happens in there, and then we will discuss the different evidences, right? So such mid-oceanic ridges are also called divergent plate boundaries, because those are plate boundaries where the plates actually diverge from each other. Okay, the plates actually diverge from each other, and that is where new oceanic crusts are being built. Okay, so what happens in such ridges? The crust is extremely thin. Okay, the crust is extremely thin. It can, I mean, at the very ridge, you know, the crust has no thickness, right? It's the surface directly lies above the asthenosphere, and from the asthenosphere you have constant volcanism. Okay, constant volcanism. So the hot molten stuff comes up. Okay, and then what happens? That kind of moves away. That moves away. Okay, and keeps on moving away. and then new stuff comes up, and that moves away. New stuff comes up, and that moves away. Now that cannot continue forever. It has to, if it is being created, it must be destroyed. Now this is what we have now described, the mid-oceanic ridge. Now, where it is being destroyed? It is perhaps destroyed in a place somewhere like this, and this is what we call a trench or a subduction zone. Yeah. So what we are observing here, that this older crust, which was once deposited here, which was once not deposited, formed here, at the mid-oceanic ridge, is this particular oceanic crust is kind of getting beneath the continental lithosphere, getting beneath the continental crust, and being destroyed, right? So this is what we call a convergent plate boundary, and the crust which is being generated at the mid-oceanic ridge gets destroyed at the trench. Okay, and you do see volcanism here at the mid-oceanic ridge. You also do see volcanism in the continental volcanic arc, through continental volcanic arcs in here as well, right? So this is essentially the mechanism of plate tectonics. This is essentially the mechanism of seafloor spreading. And because the seafloor essentially spreads, you also have the continents being drifted away from each other. Okay. So, and we will see how we can establish this process of seafloor spreading. So what happens here, if I try to put, with some bullet points? First of all, new oceanic crust is being generated, and the crusts do actually move away from, the older crust is pushed away from the ridge, and then the older crust kind of gets destroyed at the subduction zone or the convergent plate boundary or at the trench. It's the same name. So this is also called convergent plate boundary. It's written here. It is also called a trench, or it is also called a subduction zone. Okay. Now, if we try to understand this, let's just take a slide. Suppose so here is where my mid-oceanic ridge is. Okay. And here through the volcano, my molten lava is coming up. Okay, and new crust is being formed, right? And then this is essentially moving away from each other. Now, if I ask you to date these rocks, okay, what is the age? So we can essentially find, strips of rocks. So this is 0 MYA, that means this is the present day rock, right? 0 million years old rock. Maybe this is 1 MYA, 1 million year, 1.5 million year ago. This is 1.6 or so. Similarly, here you will find 1.5, right? Because, we have a seafloor spreading this way as well and this way as well. So the moral of the story, the rocks are being older as we are moving away from each other. Okay. Now, what also happens while these things are going on, the Earth's magnetic field keeps on reversing each other. Okay. So suppose right now, so this is the axis of the rotation of the Earth. Okay, this is along which the Earth is being rotated. Now, there is also another axis, which is the magnetic axis. Okay, we will talk about this. This is the magnetic axis, okay, and this is the axis of rotation. Okay. Now this angle is around 11.5 degrees. 11.5 degrees. Okay, this angle, the angle between the axis of rotation of the Earth and the magnetic axis. Okay. Now you know Earth has a magnetic north pole. I'm sure you know about it, and has a magnetic south pole, right? Now this is not constant. Throughout the history of the Earth, what has happened? So now, right now, what we are seeing, we have the north, towards our north, we have the magnetic north pole, and towards the southern hemisphere, we have the south pole, and this is what we call as normal polarity. Okay. Now this doesn't stay like it constantly. We will see what is the time period at which it fluctuates. What also happens that this north pole becomes south pole, and the south pole becomes north pole, and again after some time the south pole, this becomes north, this becomes south. Okay, so we have constant polarity reversals after a few million years or few thousands of years. Okay, so the normal polarity becomes reverse polarity, and reverse polarity becomes normal polarity. Okay. Now, say for example, today the Earth is being at this particular amount in time, this rock is being formed here. Okay, this igneous rock is being formed here, which is being quenched. The molten magma is coming up, and it is being quenched, and I see this particular piece of rock, mostly basalt, forming here. Okay, so suppose right now I have normal polarity, so I will find normal polarity here. Maybe at this time, when these rocks, the 1 million year old rocks were forming, maybe they had reverse polarity. Okay, and then again I had normal polarity, then again maybe I had reverse polarities. Okay, maybe, so I have alternate strips of normal and reverse polarities as the rocks becomes older away from the ridge. Okay, so that is what can be observed in the mid-oceanic ridge, and this is one of the fundamental evidences that such thing actually happens. Okay, let's see. Is there a question?
Yes, sir.
Okay,
So,
please. Yeah.
what actually causes the reversal of the polarity?
Okay, so that is the eddies current. It's not very well known, I can tell you that. Okay, but that is essentially the eddies current. So it is generally thought the eddies current actually let me explain. So what we have talked about, that we have right, something wrong happened. So what we have talked about, we have this outer core and the inner core, right? So what is how the outer core is? Is it fluid or solid?
Fluid.
Right. So, and you have different ions here, right? Say for example nickel ion or the other heavy metals ion, and they are with the eddies current are like moving from one direction to the other. Yeah. Say maybe right now they are moving counterclockwise, but after a while, what is being thought, that they switch from clockwise to counterclockwise motion. Okay. Now, why this happens is anybody's guess. Okay. But this is one of the most fundamental explanation that people give for which you have polarity reversal. That the eddies current actually shifts its clockwise motion to counterclockwise motion, and that's why you see the reversal in the Earth's magnetic field. Yeah, does it make sense?
Sir, but do we have any evidence that this?
Yeah, these are mostly based in modeling.
Okay.
These are mostly based on modeling and simulation.
So
No
the thing
direct
is,
evidence. Yeah.
Earth is rotating in one direction only, right? It is not changing its direction of rotation.
No, that is true.
Yeah. So why that the outer core changes its direction.
That's a hard. That is very difficult to answer. I don't think there is an answer for it, or people know about it. Yeah.
Okay, sir.
Yeah, but this is the most possible explanation that people give, that perhaps this is the reason why such reversal happens. Okay.
Yes, sir.
Okay, now such reversal is the more important part is such reversal is recorded in the ocean floor. Okay, so what you can do, what you can do, you can actually, so this is under the sea, right? So what people have done, they take vessels or boats, and then sample from these rocks. Okay, sample these rocks, and then they age them, they date them with radiometric dating. Okay, so radiometric dating. In isotope geochemistry, you will learn about radiometric dating. So generally, the process by which radiometric dating is done for basalt is argon-argon, yeah, or rubidium-strontium isotope system, or argon-argon isotope system, by which you can actually date these basalts. Okay, so by which you can say this is 1 million year old, or 2 million year old, or 3 million year old, right? And then you can also study their magnetic polarity, whether it is normally polarized or they are reverse polarized. Okay, that you can do very easily. Actually, can be done very quickly and easily. And if you plot them, you can actually very quickly see that such pattern comes up. Of course, these length of such strips or width of such strips are not constant, right? Because such reversal are not very regular. Sometimes it happens over 500,000 years, sometimes 1 million years. So because such reversals are not regular, you don't see the width of such strips, the magnetic strips on the both sides of the mid-oceanic ridge are not constant as well. Okay. So evidence of seafloor spreading and world seismicity. So what is generally seen, that because you have some sort of mass destruction, not mass destruction in the sense that the mass essentially transforms into energy, not such destruction, that the solid mass gets destroyed, the crust gets destroyed, and there is some sort of material imbalance that happens. That's why you do see earthquakes, a lot of earthquakes. So most of the earthquakes are actually concentrated along the plate boundaries. So you can see here the earthquakes which are along the plate margins, right? So you can see earthquakes along the mid-oceanic ridges. Yeah. Sorry. You can see earthquakes along the mid-oceanic ridges. You can see earthquakes along the trenches. Okay. One thing to notice, that the earthquakes along the mid-oceanic ridges are of lesser magnitude. I mean, if you do a statistics, you will find the earthquakes around the mid-oceanic ridges are of lesser magnitude, but the earthquakes around the trenches of course are of higher magnitude. Okay, why is that? You can find out those answers in Lowry's book. They are given in details. You should read those chapters and you will find that why such things are there. Now there is also comparison, what you also observe. So this provides you an evidence that such plate boundaries do exist and seafloor spreading does happen because of such a material imbalance. Okay, so this is one of the evidences that people put forward by to support seafloor spreading. Okay, the localization of earthquakes. Similarly, localization of volcanism. What we also observed, that most of the volcanoes are also concentrated along the plate boundaries. Okay, and there is very fundamental difference between the lava that comes out from the mid-oceanic ridge and from the one that comes out from subduction zones. Okay, so in the mid-oceanic ridge, what you will find, it is mostly mostly mafic magma. Mafic magma. What is mafic magma? Can someone tell me? More mafic magma and felsic magma. What is the difference?
So it's basically comprises of magnesium in mafic magma and iron winch, and in
Yes, and then the
it is
felsic magma is
silicates.
more
Felsic
silica
will be
rich.
Yeah,
silica rich.
silicates.
Okay,
Yeah.
so can you guess why such things do happen? I mean, why you do see more mafic magma coming out from the mid-oceanic ridges and more felsic magma from the subduction zones? What is your guess?
Since it comes from a deeper part of the crust, like, it's directly, like, it comes from mantle. So,
Yeah, so that is, well, that's not quite it. What happens in case of the magmatism that happens in case of the trenches or the subduction zone, it gets mixed with the continental crust, right? So what continental crust consists of? Granite, right? Which is more felsic. So that's why your
yes.
magma is also more felsic that comes out from the subduction zones. Okay, and comparatively, you have more tholeatic, more peridotitic magma coming out from mid-oceanic ridge, right? So this is not exactly the context, but if you think about, I'm sure you have read about the mid-oceanic ridge basalts, the andesites. If not, you will read them more in your igneous petrology lab, and you will see that the characteristics of magma is very different. Is very dependent on the tectonic setting as well. Okay, so depending on the plate boundary, the nature of magma actually changes. Yeah, a detailed description also is also given in Lowry's book, so you must read that to enhance your knowledge. Of course, you will learn them with more details in your igneous petrology class. But let me just hint you that the nature of magma and the nature of volcanism, the nature of earthquakes that happens are very different from one boundary to the other boundary. Okay? Mid-oceanic ridge has a different type of boundary. Sorry, magmatism and volcanism. Volcanism and earthquakes compared to the subduction zones. Okay. So this is what we have just talked about. You know what we are seeing. So the color. So these are the sea floors which are being shown here, and the color represents age. The hotter color, like the red, the hotter color represents younger age, and the cooler color represents older age. And as you can see here, of course, the youngest rocks are close to the mid-oceanic ridge, and as you are moving away from the ridges, the crust becomes, the oceanic crust starts to become older, and of course, at the farthest point, we have the oldest crust, oldest oceanic crust, and this is what we have just talked about. And this is also, we have talked about, this is the geographic North Pole, this is the geographic South Pole, through which my Earth is, this is the rotation axis of the Earth, this is the magnetic field of the Earth, which is kind of shown as a dipole, and then you have the magnetic North Pole and the magnetic South Pole, which is making an angle of 11.5 degrees. But remember, this 11.5 degree also changes. We will see that later on when we discuss magmatism. Okay, and this 11.5 degree also changes. This actually can be all the way up to 3.5 degrees, maybe up to 17.5 degrees or so. But right now it's 11.5 degrees. And what essentially happens, this magnetic North Pole essentially wobbles around the, this is what it does, this magnetic axis wobbles around the rotational axis as well. Okay. So this is not fixed. So this axis keeps on rotating along the rotational axis of the Earth. Okay. But this solid angle, this is solid angle, right? The solid angle is around 11.5 degree currently, but it changes. Okay, and this change is called, this particular change 11.5 degree, 3.5 degree that we talked about is called secular variation. This is what we call secular variation. Okay. So, and of course, this is the change is there, this change is there, but also this is like right now North Pole and South Pole normal polarity, but then this will not stay like that forever. We do see the North Pole, transform into South Pole to North Pole, and then this will not stay also forever. That reversal will continue. Okay. So the time spans of magnetic reversals are randomly distributed, as we said, with most being, yeah.
So, is there any fixed range of degrees? How much degree it will there will be between the magnetic axis and the geographical axis?
No, so we will discuss that in later on. What I have just said, it varies from all, I mean, around 3.5 degrees to 17.5 degrees. That is what we have seen from the record that we have. Okay.
Okay, sir.
Yeah, we will discuss it in later chapter with greater details. Okay, but to answer your questions, there is no fixed pattern. So the time spans of magnetic reversals are randomly distributed, with most being 0.1 to 1 million years, with an average of 450,000 years. Okay. So this is what I was talking about. Earth has magnetic field, probably caused by the rotation of the solid inner core. Rotation of this solid inner core in liquid outer cores, both mostly iron. When rocks cool at the Earth's surface, they record Earth's magnetic field, as we just said. And as a result, we do see this polarity reversal. This is the ridge. We have the normal polarity and reverse polarity, normal and reverse polarity. Okay. And that is one of the evidences of seafloor spreading. Okay. So any other question? So why does then, so together with seafloor spreading and continental drift, that constitutes your plate tectonics. And why does plate tectonics happen? So the plates are actually called the lithospheric plates. Okay, so lithosphere is the place where, so what constitutes the plates are the lithospheres. Okay, as the part of the upper crust, right? And then what we are observing, that why such plate tectonics would happen? Simply because I do have convection cycle in the mantle. Okay, so convection cycle in the mantle. Why does convection cycle do take place? Because I have a thermal disequilibrium. Okay, so thermal disequilibrium means if we are moving, so say for example, this is my Earth, okay, and as we are moving down, of course, the temperature keeps on increasing, right? So at the very beginning, it's around 30 degrees centigrade per kilometer in the crust. And then the rate actually changes, which is called adiabatic rate. We will talk about it later on. For the time being, just consider 30 degrees centigrade per kilometer. So the temperature becomes higher as we are moving down, right? So this place, say for example, now this is my lithosphere. So this is my lithosphere. So this part is of course hotter and this part is of course cooler. So there is a thermal imbalance. So if I have a thermal imbalance, say for example, if we look at this beaker experiment, because I am hitting it from the bottom, so the warmer particles, water particles want to move up, the colder ones want to move down, simply because there is a density difference. If we heat a fluid, the density decreases. So the lesser denser material wants to move up, and the denser material actually wants to move down. So the same thing actually happens. I have a cooler cooler upper part of the mantle and hotter lower part of the mantle, and that's why this thermal instability essentially gives rise to the convection cycle. Now, whether the convection cycle is only restricted in the asthenosphere or it goes all the way up to lower mantle is anybody's guess. People have different theories. Some people say that it is only restricted in the asthenosphere. Only the convection cycle is only restricted in the top part of the mantle. Okay, and that is the most believed hypothesis, that the convection cycle is only in the upper part of the mantle. Okay, but some people do believe that there is another deeper, convection cycle that do exists as well. So it's like a double wheel mechanism. Okay, but then the most accepted hypothesis is it's restricted in the upper part of the mantle. Okay, and because of this thermal instability, of course, the mantle expresses. So it wants to come to equilibrium. It wants to
Sir, could you explain what is the driving force for this convection mechanism?
the thermal instability, as I said. So what I have just said, that you have hotter. I mean, if we are moving down the crust, what is happening? It becomes more hotter, right? So I have a thermal disequilibrium, right? So if there is a thermal disequilibrium, what it tries to do? It tries to come to an equilibrium. And what are the processes by which it can come to an equilibrium? Say, for example, in case of a solid, the thermal equilibrium is achieved by conduction, right? That is how the heat transfer happens. In case of a fluid, the thermal equilibrium is achieved by convection. That is how the heat transfer happens. The material itself actually moves. You know about this, right? You have studied this in your high school physics.
Yeah.
Isn't it? Yeah. So that is essentially the driving mechanism, that you have a thermal instability. The lower part of the mantle is hotter than the upper part. So if there is a hotter thing which is sitting down and cooler thing which is sitting up, what would happen? The hotter part, the hotter, less denser thing would try to come up. Isn't it?
Yeah.
And the cooler thing try to go down. So and that is what the convection cycle is all about. That thermal instability is the driving mechanism.
Okay, sir.
Okay, is that clear? And because the thermal this convection cycle actually happens, it's like if you have a ball which is rolling, and if you put a plate on the top of it, if you put like a slab on the top of it, the slab actually translates. Right? You understand my point, that if I have a slab, like a solid slab, and here I have a ball, and this ball is rotating, what would happen to the slab? This slab would translate. Right? So think about this rolling ball to be the convection cycle. And that is being initiated because of the thermal instability. Okay? And because of the rolling of the ball, I have the translation or the movement of the plate. Okay. So any other question?
Yes, sir.
Yes, sir.
Yeah.
Pritam, you can go ahead.
Okay, sir. So, if this is happening, if this is true for the asthenosphere, then this principle is true for any fluid, right? So, why it is not true for the outer core? Means, in that case, also, if we go deeper, then
no. What generally is seen, that the upper mantle is actually solid. Okay. Sorry, the lower mantle is solid. Okay, this is solid lower mantle. Okay, and you have this fluid here, and then there is another solid. Now, whatever movement supposed to happen would be restricted here, right? Because this is solid and this is liquid. That's why people do think that because the lower mantle is very compressed and solid that there is perhaps no convection cycle in the lower mantle. It is only restricted in the asthenosphere.
So means I am telling about the outer core. Means
Yeah,
the
that's what
liquid.
I said. So it's like a fluid sandwiched between two solids. Why would there be convection between them?
But isn't movement in the outer core the reason for the geodynamo?
Yeah, that is what I said, na? But it is within the outer core. It is within the outer core. He is asking whether we can have like a mixing between the lower mantle and
No, sir.
outer core, right?
I am telling that the same convention cycle
Yeah,
can it happen in outer core? Means since it is happening in
it could happen, but who knows? Nobody, but it could happen. Yeah, but that is not something that affects plate tectonics.
no, sir, not about plate tectonics. I think that may be the reason of geodynamo also because
Yeah,
the
so that is so there is a movement of the but there is a movement of the charged particles in the outer core. The substance which are present in the outer core, which is at a very ultra high pressure temperature, and it is very difficult to figure out how the fluid will behave at that particular temperature and pressure. Okay, it's
yes,
very
sir.
difficult to it might not behave exactly like it behaves in case of the asthenosphere.
Yes, sir, I understand. Yes.
Yeah, it's almost I mean it's as I mean it's very high. It's almost at the state which is unimaginable by what we can think of, any natural phenomena that we see around us. Yeah, outer core is extremely hot and high, very high pressure. Okay,
Sir,
any other question?
hello. Am I
Yeah,
audible?
yes.
Yeah, sir. In these convection currents of the mantle,
Hmm.
does density play any role? That means as a lower mantle is more denser than the upper mantle for convection
Hmm.
currents
Yeah, so
instead of thermal instability.
no, I mean the density is a function of thermal instability, right? Because and the very high dense upper mantle is because not because exactly because of the temperature, it is because of the pressure. It's at a very high pressure. That's why such thing, being it at that high temperature, still remains solid because of the very high pressure. Okay, and the dense, I mean the convection cycle is fundamentally attributed to the density difference, right? But the density difference is attributed because of is attributed to the thermal instability.
Okay, sir.
Yeah, anything else? All right. Okay, so all right, so we will in the next. So tomorrow, what I will do, I will actually upload a pre-recorded lecture where we are going to talk bit more details about plate tectonics and slowly you know about these things about three types of boundaries and slowly get into the concept of something called triple points. Yeah, and we'll do some mathematics around it in the next week. Okay, so tomorrow I will upload a lecture. All right, so I stop it here then. If you have any question or further any, have more discussion around what we just discussed, we are free to do. Anything else?
Good morning, sir. Uh,
Yeah.
I wanted to ask if it would be possible to change the slot for this course.
No, that's too late. Why?
I actually have another course in this same slot. I'm not from ES major, I'm from bio major, but I wanted to take this course since I wanted to do a minor in ES, and this course
Okay,
is
but yeah, but
multi-branch.
that is not possible. I'm sorry for that, but that's how it is.
Sir, so if we have clashing slots, is there any other way to resolve apart from shifting?
What do you suggest?
Um, Sir, since you're taking two lectures on the first 2 days of the slot, if
Mm-hmm.
the other course will take their live lecture in the third day of the slot, and then the only clash that remains would be for the NSEM exam. So if you could agree to take that on a separate time from the NSEM exam of the other course.
Well, see, the thing is that I don't decide these things. Okay, I if such thing, if it is only on my hand, I am happy to do it. Okay, but it's a very intricate system which is mostly controlled by DOA and
Sir,
our
because
DUGC.
actually the problem is that
Yeah.
earlier on the bio professor decided to, like, he agreed to change the slot, but then he went back on his word. So that is why we wanted to ask if you would be willing to make the adjustment as well.
Now, changing the slot is not possible. That is not something I can do. But changing exams, that is perhaps a possibility, but that you have to discuss and get agreement from our DUGC as well as from DOA.
Dua.
Okay, but
Okay.
that's not in my hand. Changing class slot is not possible because there are plenty of things which are kind of dependent upon the class slots and other engagements that I have and everything. So yeah, it's very difficult. I'm sorry for that, but yeah. But certainly
Okay,
one day
sir.
exam is not a big deal. I can adjust, but that must be a decision of the DUGC and DOA. Okay.
Okay. Thank you, sir.
Yeah, I'm sorry for that. I want to be more flexible, but the system doesn't allow me to be. Okay, so I stop it there here. Then I will upload a lecture tomorrow. Okay. I hope you have all subscribed to my YouTube channel.
Yes, sir.
Yeah, because I will not send you links of individual lectures. Okay, you will find it there, and you will yeah, you should do it from there. All right, then I'll stop it here. Thank you.
Thank you, sir.
Yeah.